Hello guys, how are you doing? I'm Mohammed Sadri. The title of this video is PL reconfiguration in PetaLinux. This is actually something very simple, and our target is ZYNQ Ultrascale Plus. Basically, our tests are being done on the ZC102 board, and this is the second video I am creating for this series, in which it focuses on reconfiguration of the PL device tree overlays and on the basically remote firmware update. And this is the second one. It focuses only on PL reconfiguration. It's very simple, straightforward. And so let's get started. I have a Vivado project here, simple Vivado project. I have created a simple memory mapped based IP. It contains an AXI slave plug, and then what it does is a simple, very simple mass operation. So basically it has a C operation parameter. If C operation parameter is 0, then what it does, it sums up the first two registers that are located inside the IP, and if this one is 1, it multiplies the first two registers. So for this test, for checking PL reconfiguration under PetaLinux, what I'm gonna do is I will create two Vivado projects. In one of the Vivado projects, this parameter here is 0, and in the other Vivado project, this parameter is 1. And for both of them, I go ahead and create the bit string. So basically, one of the designs, it performs a summation operation. The other one performs multiplication. Then I develop a simple Linux kernel level driver for my IP. Also, I develop a simple user level application. And then I will show how we can reconfigure the PL on the fly while the board is running. So in our test, basically when we boot the board, the IP, the configuration of the PL will be this one. Basically the IP will be summing the numbers that we are giving it. And then as we will see, we reconfigure the PL in PetaLinux, and as we will see, the operation of the IP will change. This video does not talk about really device tree overlays. Here, basically, the device tree is not changing. The arrangement of IPs that we have inside the PL, they are not changing. The device tree is not changing. It's not really happening that I need to change the driver, the kernel level driver that I have developed for this guy. So the kernel level driver stays in the kernel as I am reconfiguring the PL, and basically I use it again after the PL is getting reconfigured. In future videos in this series, I will show you cases in which the arrangement of IPs in the PL change. A new IP appears in the PL, and so the device tree gets updated, and as the device tree gets updated, the drivers should be loaded into kernel or unloaded from the kernel. So this is for future videos, but right now we have a simple design. We want to reconfigure the PL. So what do I have for this project? I briefly here show you the project folder structure. Yeah, so it's already being done. It has a doc folder, downloads for not important. IP contains the IP that we have developed. Briefly, we will look at it right now. Then we have a backup of the SD card that we use for this project. Then we have our PetaLinux folder. Then we have a script folder, which this folder contains basically those scripts that we put on SD card, and these guys are responsible for reconfiguring the PL. I will show you the internal content of these scripts shortly. And then we have two Vivado projects, as I described to you. The first Vivado project is the one that performs summation. The IP performs the summation operation. And the second Vivado project is the one in which the IP performs multiplication. Okay, so this is our folder structure. And I have created the Vivado project. I have generated the bit stream for the Vivado project. And when you want to reconfigure the PL, basically module, a kernel level module called FPGA manager in PetaLinux will be used. And the bit stream that you want to put on the PL will be given to this module. Now, the bit stream that you give to this module should have a specific format. So the .bit file directly cannot be given to this module. It should be .bin file. So you need to use the bootgen tool of ZYNQ to convert this bit stream file to a binary file that the FPGA manager understands. And so this conversion is very simple. If I go to my one of the Vivado projects, for example here, I would like to, if possible, I would like to make this guy a little bit larger, but I'm not sure if I can do that. Yeah. So, but this is not what I want. Anyway, I want to show the content of that script. So here we go. So here is our script. Basically, it calls the bootgen command, gives the a bif file to the bootgen command, and then it produces the output binary bit stream that can be given to the FPGA manager. So very important is obviously the output.bif file. What's the content of this file? I'm gonna go inside more output.bif. So this is the output.bif file. All you're putting inside the output.bif file is the bit stream, and then this is basically the bit stream that is being generated by the project, by the Vivado project. So this is the bit stream that's being generated by the Vivado project. This is the file that is the outcome of this generate boot.sh script, and again here is the generate boot.sh script, which is a very simple script, and all it does, it gets the output.bif file, it gets this file, it gets the bit stream, and produces basically a bit stream which can be given to FPGA manager, and that can be used for reconfiguring the PL. Now, the same thing also exists for the other Vivado project. Okay, so we have these two bin files, and obviously I will put the bin files on my SD card, and the SD card will be placed in the ZYNQ102 board, and then we will, in action, I will show you how they can be used. Okay, so I go back to my top level project. I want to briefly look inside the IP folder. Inside the IP folder, we have a simple memmap IP, and inside the simple memmap IP, we have a RTL source folder. arterial source folder basically contains the source code for our memory mapped IP in Verilog, and the operation of the IP is very simple. I can show you how it's basically working. There's a parameter. This parameter is called C operation, and this parameter C operation is the guy who decides in the code what operation should be done on the registers of the IP. So basically this IP reflects the summation of register 0 and register 1 on register 2 if C operation is 0, and if it's not 0, it reflects the multiplication of register 0 and register 1 on register 2. So basically, if I write to this IP to the base address and base address plus 4 two numbers, then if the operation is 0, when I read base address plus 8, what I get is summation of these two registers, and if the operation has been 1, then what I get is the multiplication of the registers. So what we are gonna test is basically we have generated two beta streams, one with C operation equal to 0, another one C operation equal to 1, and then as the system is operating, we are reconfiguring the PL with either one of these two beta streams, and we will check the operation of the module. Okay, so this is the IP we are using. We will see it in action soon. And then I have the PetaLinux folder, and inside the PetaLinux I have created a Linux kernel level driver for my module, a very simple one that allows me to program these two registers, register 0 and register 1, and then read back the third register, register 2. And also I have created a user level application, and user level application is basically talking to the kernel level driver using IO controls. So obviously, if you are familiar with the folder structure in PetaLinux, you know that the driver is located inside project spec, meta user, receipts modules, and then the name of the driver that I have, and then again the name of the driver.c. Extremely simple driver. You can look at the source codes related to this video for the complete driver, but the key part is this IO control, which is one of the file operations, and I have implemented that. And the IO control provides basically three IO controls: one for programming the first register, another one for programming the second register, and then the last one for reading back the result, which appears on the register number 2, let's say third register. Okay, so you can look at the complete driver when you have the source code. And then we have obviously receive apps, and inside receives apps I have created my simple app, and my simple app again is a very simple C source code which is basically responsible for talking to the driver. Extremely simple. Right now I am calling basically the IO control 3 times. First time to set the value of the first register, next time to set the value of the next register, and then last time to read back the result, and then I'm printing out the result. And this is my Linux setup, and I'm gonna run this on ZYNQ 102 shortly. And very simple. There's nothing complicated right now. So I have created, if I go inside images Linux, I have created our boot.bin. I have created the image.ub, and I put these two files on the SD card. I have a copy of the files that I have put on the SD card here, SD card backup, and this is good to look at. This is basically a copy of what we put on the SD card. This is boot.bin, image.ub. Obviously, these two guys are responsible for bringing up the PetaLinux. Then I have two scripts. The first one is named go to design 01. The second one is named go to design 02. Basically, if you run go to design 01, it programs the PL with the first design, with the first Vivado design, in which C operation is 0 and it performs the summation operation. And if we run, then when we are running this thing on ZYNQ102, if we run this one, the second one, go to design 02, basically it reprograms the PL with the second design, and there we are using multiplication. Okay, no, so how the register, the script looks like. The script is very simple. A set of operations basically defined by ZYNQ. First of all, we are telling the FPGA manager, which is the guy who is responsible for reprogramming the PL, we are telling him we are programming the entire PL. We are doing a full programming of reprogramming, reconfiguration operation. And then we create the folder that we need for our firmware, let's say the beta stream that we want to put on the PL. And then after that, we are copying the beta stream there, and then we are going to that folder, and then we are giving FPGA manager the beta stream. This is the script that we run. And obviously for the first design, I'm gonna give FPGA manager the first beta stream, and for the next design the second. So this is the difference between these two scripts. The only difference is I'm giving him a different beta stream each time. And inside these two folders, Vivado design 01, Vivado design 02, I have the two beta streams. Okay, so let's run this thing and see how it works. My expectation, this is a log after run. I run everything again. So I'm turning on the ZYNQ102 board, and obviously it takes, it's not right now connected to the network, so it takes a little time so that it comes up, and after that we can test our design. So if I go back to the main project folder, one thing I want to tell you is inside PetaLinux, you need to make sure that the kernel is compiled with support for FPGA manager. Okay, so also if in later videos, as I will show you, we use device tree overlays, you need to make sure that the kernel is also compiled for device tree overlays, and that's a good idea to double check this. When you we are using right now PetaLinux 2019.1, Vivado 2019.1, and by default, based on my experience, by default FPGA manager, device tree overlays, they are all enabled in the kernel. But maybe this is a good idea if you double check this. Okay, which is obviously this can be done by issuing the PetaLinux config -component kernel. Okay, which brings up the menu interface through which you can configure the kernel, enable, disable different drivers inside the kernel, and there in device driver section in FPGA device programming section, if I recall correctly, you can double check if FPGA manager is activated. So I'm going back to my ZYNQ102 board console. Here we are on ZYNQ102 board console. I log in, I mount the SD card that we have, because all of the files that we have are there. So these are the files that we have on the SD card, and we are on the ZYNQ102 board. And as you remember, I created some, here is the menu through which you can configure the kernel. We will talk about it later. Right now I don't think this is necessary. Let's continue with the test we want to do. So I developed a simple app. As you remember, my simple app, and this guy is responsible for talking to driver. Yeah, so this guy is responsible for giving the numbers to the driver, and the driver will program the numbers into our IP, and then getting back the result. So when I run it, here is our printf statement. User level, we have written values 2 and 3 to register 0 and register 1, and then we are reading back register 2, which is obviously the summation of register 0, register 1, which is 5. Okay, now this is obvious. Now if I run the go to design 2 script, so I say go to design 2, and I showed you the content of this script. Now I expect that the PL is reprogrammed with the new design in which the IP performs multiplication and not summation. So if I run my simple app again, I should see the result of reading back register 2 is multiplication of 2 and 3, which is 6, and this thing is working fine. Now if I go back to design 1 again, reprogram the PL with design 1, if I run the app, I expect to see 5 again. So the rest, for your reference, the rest of the print messages you see here, they are coming from the driver. You can, when you have the driver source code, then you can edit the driver and remove those printf statements if you don't like them. Okay, so but anyway, our PL reconfiguration is working perfectly fine. Okay, now for the ending part of this video, here is the Linux kernel menu config. There's a device driver section. Obviously you go to device driver section, and then there is device tree and open firmware support, and make sure device tree overlays is enabled. In this video I didn't use device tree overlays. My driver didn't change during reconfiguration of the PL. The arrangement of IPs I had inside the PL, they didn't change. So I really didn't use this one, but I will show you in future I will use this one, and I will show you in future we have a design which when you reconfigure the PL, the device tree changes. The device tree should be basically scanned again, and the drivers should be loaded when they are needed. So, and then if I recall correctly, if I scroll down a little, somewhere down there I should be able to find the section related to FPGA configuration framework. Okay, so inside FPGA configuration framework, make sure that FPGA bridge framework is enabled. Okay, And yeah, so by default they are enabled. I didn't change anything in the configuration of the kernel. Okay, and that's it. So we exit after we make the change, and obviously we should recompile PetaLinux. Yeah, so I think I covered most of the important content. We looked together at the hardware, we looked at the software, we tested our design on the board. The design works fine and is stable. And yeah, we are at the end of this video. Thanks for watching. See you in the next video. Bye.